Okay, so now we're going to just talk a little bit about the kinematics of rigid bodies. And you're going to notice that there's a lot of similarities between the kinematics of rigid bodies and the circular and spherical motion stuff that we did. And so I want to first point out why that is. So it's very similar to the circular and spherical motion of particles. So why is that? And the answer is, so if you have a rigid body like this, and it's rotating about some point, okay, think about the individual particles that make up the rigid body and what motion they're going through. So if you just arbitrarily choose this point here, as it rotates with the rigid body, it follows a circular path around the fixed point. And if you don't have a fixed point, the same is true about the center of mass. And so when we're talking about rotations of rigid bodies about either the center of mass or a fixed point, we're really talking about circular motions of each of the individual particles. If we looked at a different particle, you'd have the same thing happening, just a different circle. So each particle follows a circular path. If you represent the angular position of a rigid body about its axis of rotation, by the value theta, then d theta dt is equal to omega, and d omega dt is equal to alpha. So this is the angular velocity and the angular acceleration. This works in 2D. For any rotation. But in 3D, sorry. So in 2D, you can use this idea of theta, omega, and alpha for any rotation. But in 3D, like I mentioned before, there's no such thing as a theta vector. So there's no such thing as an angular position vector. So for general 3D motion, all we know is that the derivative of the omega vector with respect to time is equal to alpha. So, yep. You have to be careful with those. I have to think about that more, but you have to be careful with cylindrical and spherical coordinate systems when you're taking derivatives, because those are non-inertial coordinate systems. You know, like because the axes are rotating with the object. And so a lot of times when you take your time derivatives, and we'll see that when we talk about spherical and cylindrical, you have to deal with that fact. So I'm going to guess no, but I'd have to think about it more. Okay, so in 2D and 3D, remember that omega is really a vector with its direction along the instantaneous axis of rotation. And its direction then has to follow the right-hand rule. To express a 2D omega vector, you can always use 0, 0, omega. Okay, so we talked about that a little bit already with circular motion. 2D. Well, so if you're dealing with a two-dimensional motion, then to represent it as a vector, it's always 0, 0. So yeah, when we deal with rotations, even if the motion is purely two-dimensional, we're going to have 3 components on our vectors, because now the rotation vectors are going to be out of the plane. And so if you're in the xy plane, your rotation vectors are going to have 2 0 components and then a non-zero component z. Okay, so I want to just draw 3 rotations and have you think about what these vectors are. Okay, so say that this is your coordinate system, and let's say that you have a rotation this way. If the magnitude of omega is 1 radian per second, what's the omega vector? Okay, so yeah, so if the rotation is that way, the right-hand rule says that, you know, for your fingers to rotate that way, your thumb's pointing in the positive x. And so the omega vector for this one would be 1, 0, 0. Okay, how about this one? That's in the negative y direction because your fingers are going this way. And so that's 0, -1, 0. You can't tell which way I was trying to make it go. Yeah.
Is it going like?
It's supposed to be, yeah. It's supposed to be like going to the right behind the axis and then to the left in front, you know, like this.
So it's coming out in the positive x.
Yeah. Okay, and then here's the one that's a little different from those. So what about this? Where this angle is 45 degrees. So if something's rotating 45 degrees off axis like that, what's that omega vector going to be? Yeah, well, it's going to be pointing in. So the right-hand rule says it's going that way, right? So that's going to be cosine and sine of like 225, or yeah.
Couldn't you also think of it as like it being like horizontal and then like doing the right hand rhythm multiplying by sine cosine with the angle?
Yeah, you can. So basically, that would be using the rotation matrix. Yeah, you can do it that way. But so this one, this is 0, -1, 0. And this one is -0.7071, -0.7071. And what if instead of having a magnitude of 1, it had a magnitude of 50 radians per second? What would the vector be? Just 50 times this. So, you know, 35, -35, -35, 0. One thing that's important to, like an important distinction between these rotational quantities and the translational quantities is those translational quantities, position, velocity, and acceleration, vary for different points on a rigid body. Like, for example, if you have, say, what? Yeah, quantities. If you had a big metal arm, so that's a rigid body, and say there's a mass on the end here or whatever, and if this is rotating through a circular motion, what's the velocity of the point right at the axis of rotation? 0. The translational velocity is 0. The velocity out here is big, right? Whatever, it depends on how long it is and stuff. But whatever the angular velocity is at this point, it's the same as the angular velocity here and here. Okay, so the translational quantities vary point to point. The rotational quantities are just true of the entire body. Okay. So they hold for the whole body. Once you know the angular acceleration and the angular velocity of a rigid body, you can calculate the velocity and the acceleration of individual points on the body using the equations that we were using for circular and spherical motion. Velocity is equal to omega cross r, and acceleration is equal to alpha cross r plus omega cross r. So just like we did in circular and spherical motion. And the reason it's just the same is because, like I said, each individual point is following a circular or spherical path about whatever your fixed point is, your axis of rotation. If the rotation isn't about a fixed point, then it's usually going to be about the center of mass. And the calculation you do is the same way we did it when we talked about like circular motion that's fixed to some other thing that's moving, where you use the relative motion equations. So the velocity of p relative to O is equal to the velocity of p relative to A plus the velocity of A relative to O. And the same thing with acceleration. Okay, so here's an example problem. So say that you have this rigid body. Doesn't matter what the shape of the body is. And let's say the center of mass is over here. And we're going to use a coordinate system with x horizontal, y vertical. And let's say P is over here. We want to figure out something about this point, and It's a distance of 0.3 meters from the center of mass. The angular velocity is -6 radians per second. The angular acceleration is positive 14 radians per second. And this thing isn't rotating around a fixed point like a hinge. It's rotating about the center of mass. And let's say that we know that the velocity of the center of mass is 10.5. And the acceleration of the center of mass is -8.4. And we want to know what's the velocity of that point P and what's the acceleration vector of that point P. So what we're going to do is we're going to first imagine that the center of mass is fixed, use circular motion equations to calculate the relative velocity and acceleration as that point moves through this circular path. And then we'll just add that using the relative motion equations to these to get the total velocity and acceleration. So first, the velocity of P relative to the center of mass, or the velocity of P assuming that the center of mass was fixed. That's omega cross R. What's omega as a vector? Yep, 0, 0, -6. What's the R vector? Yep, so in the negative x direction, so -0.3. And then 0, 0. Take that cross product and you get, and then positive, right? So it's -6 times 0.3 and then negative because it's y. So it should be positive, I think. Yeah, and yeah, so physically, this is rotating clockwise, and so the velocity needs to be straight up. And so now the total velocity, we want the velocity of P relative to the origin or the ground. That's equal to the velocity of P relative to the center of mass plus the velocity of the center of mass relative to the ground. So that's 0, 1.80 plus 10, 5, 0. So the velocity of P is 10, 6.80. Yep, that's instantaneous. And for the most part, these kind of problems, you're always just going to be dealing with instantaneous velocity because if you have a function for that R vector, right? I mean, in order to come up with in order to use this equation to come up with a functional representation for v as time changes, you need to have a functional representation of that r vector, right? But if you have a functional representation of that r vector, you could just put your origin or your coordinate system there and just take the derivatives. And so usually this would not be the easiest way to go if you had a functional representation of r. Okay. So usually that's just, you're doing this instantaneous. All right, so now acceleration. What do we expect for the acceleration components? Is there going to be tangential acceleration? Well, we have angular acceleration. So that means there's going to be tangential acceleration. Or another way of saying is this speeding up or slowing down the rotation? Slowing down. So there has to be a tangential acceleration that's opposite the velocity vector, which means there should be a tangential component pointing down in the negative y direction. And then there's always centripetal acceleration, so there'll also be a centripetal component in the positive x direction. So we expect positive x, negative y. Okay, so the acceleration of p relative to the center of mass is alpha cross r. Alpha is 0, 0, 14. The r vector is negative 0.300. And then the omega vector is 0, 0, negative 6, crossed with the quantity 0, 0, negative 6, cross negative 0.300. So that should be 0, negative 42, 0, or 4.2, right? And then this should be what? Oh. And then this one is the velocity vector that we had before. So that should be 0, 1.8, 0. Add those two together, and what do you get for a total? Anyone done with that?
10.8, then negative 4.2, then 0.
This is, okay, so 10.8, negative 4.20. Okay. So here's the tangential acceleration component. It's in the negative y like we expected. Here's the centripetal. It's in the positive x like we expected. And then the last step is use the relative motion equations. So the acceleration of p relative to the ground is equal to 10.8, negative 4.20, and then add on the acceleration of the center of mass, and you get a value of 2.8, negative 0.20. Any questions about that? Okay, so that's pretty much all I'm going to say about kinematics of rigid bodies. But there's a set of problems to work through. But I think you should be able to do those. And then next time we'll start talking about kinetics.